hold on to both. Good morning. Okay, left and right. So thanks for organizing this amazing workshop so far at this stunning place. I thought it would be fitting to start the school today with a sobriety test. So those of you who think this is blurry, or you think this is surprising, or those of you who can no longer remember this pie chart, I think you should stop drinking immediately, or at least wait until after breakfast for your first tequila. So I thought I'll again start with this pie chart, which hopefully everybody has seen many, many times before. The fact that most of the universe is dark. And I think the latest WMAP5 may have this at 72 and this 4.6 or whatever. But the message here is the stuff we are familiar with, you, me, stars, all the stuff in our brain that we don't know much about, and even antimatter, they all go into this tiny budget called atoms. And most of the universe is dark, and part of it is in what we think is cold dark matter, and the rest of it is in dark energy. And I'm sure there will be many talks to come covering all the ranges of mass here. But I thought I'll go into a little more detail in today's lecture in the dark matter sector, and to remind everybody that there are actually two dark matter problems. In today's economy, especially in California, we keep talking about deficits. So I thought one could take a more optimistic view here. Often we talk about the missing matter, missing energy, as if there's some deficit of something. But the fact is, if you take an optimistic point of view, there's really a surplus of a bunch of stuff that we don't know. We don't seem to need them, dark energy and dark matter. So I would like to call this the energy matter budget surplus in the universe. Now, if you actually go out and try to count, try to observe stars and gas and so on using telescopes or satellites, the bottom line is you try to add them up. For example, stars and neutral gas in galaxies. All the luminous baryons we can detect doesn't even add up to 1% of the critical density. You may think clusters have a huge amount of hot gas, which is true. And the hot gas fraction actually is comparable to the cosmic baryon budget. But clusters are so rare that the amount of baryons in clusters is not the dominant place where baryons occur. So most of the baryons probably that we observe, we have seen appear to be in galaxies, but this number is tiny. But from the Big Bang nucleosynthesis and the cosmic microwave background and anisotropy power spectrum, we now know that the atom, the sliver in the pie chart, is about 4%. So this difference, the fact that the omega baryon is much, much bigger than what we can measure right now, is actually the first baryon. I will call this the first dark matter problem. And the difference implies that there must be dark baryons out there. And I put the dark in quotes because presumably it's dark because we just haven't been able to detect them through, with current sensitivity in the satellites and the telescopes. And probably a lot of you remember the searches such as the Macho searches in the 90s looking for compact baryonic halo objects. And they were mostly searching for cooled white dwarfs, Death stars, which are most abundant form of Death stars in our galaxy or galactic halos, which are just sitting there and fading away. The idea there was maybe there are so many of them that they could account for this budget surplus. But the Macho experiment indeed, and other Ogle and there are a few teams working on that through microlensing, they indeed found microlensing events that could be attributed to faded white dwarfs but the number density simply didn't add up. So I think the current, so this is still a mystery in the sense that we haven't discovered all of it. And I think the current guess is that at least half, 50% of this baryonic budget would reside in some sort of what's called a warm-hot intergalactic medium, gas of 10 to 7, that's probably mostly in between galaxies or in the group environment or in the outskirts of galaxies or even in superclusters in the medium sort of bridging clusters. These sort of diffuse component of gas, which is not quite, is in the soft X-ray range, but it's not quite in the hot gas, like 10 to the 7 or 10 to the 8 Kelvin gas we have seen in rich clusters, but rather the outskirts or in the bridges. That's where simulations, at least, are suggesting. Now, there are a number of recent results looking for such gas, either in emission or in absorption, in particular in absorption in oxygen-6, absorption lines in the ultraviolet, or oxygen-7 in the X-rays. And there have been a number of papers claiming detections of such components. And I think some of them are trustworthy. However, currently it's not clear for every case that whether the gas actually really exists in the intergalactic component, or it's just right outside of the galaxy, because some of the redshifts are extremely close to the existing galaxy. For example, even in our local group. So there, and the emission, I think, detection claims are at a lower sigma level. So it's still interesting. I think this is still a puzzle, and we haven't quite discover all the baryons that's missing. Okay, and that's all I'm going to say about the baryonic dark matter problem. Maybe there will be some contributed talks on this later. However, I want to turn to the non-baryonic dark matter problem, the second problem, and that's the more well-known problem, the fact that omega in matter, so here I've added up the 4% to the 23% in the pie chart. That's what we usually refer to, and there's 27% of the critical density in omega matter. And this gap, which is again huge or even larger in absolute value, implies that there should be non-baryonic dark matter. And here are some of the candidates. I think the most promising current candidates are the neutralinos, although axions, there are still searches looking for axions. And massive neutrinos now appear to be just a sprinkle of the budget. It's ironic that neutrino oscillation experiments finally revealed positive detection, implying very interestingly that neutrino masses are indeed non-zero, but the masses appear to be very, very small. So in the omega budget, massive neutrinos only add very little to it. But we can still constrain neutrino masses using the precision cosmology measurements we have today. But the primary candidate is our neutralinos, and that's the cold-dark matter component. And I'm sure Eric will go into much detail about the dark energy component, and the cosmological constant is just one possible candidate. And I will not say any more about that in this talk. So this summarizes the two dark matter problems, the dark baryonic problem, dark non-baryonic problem. Now I would like to go into some more detail about how we can actually go about making predictions theoretically about the growth of structures in the universe. So I kind of think of this for pedagogical reasons, such calculations to fall into three regimes. One is the absolutely homogeneous isotropic universe, which these numbers represent. They represent the absolutely spatially averaged energy mass density. So knowing these numbers and using the Einstein equation, one can solve to zeroth order, meaning assuming imperturbations, assuming the universe is completely homogeneous and isotropic, then you can use the Robertson-Walker-Friedman framework and solve for the overall kinematics of the universe, such as the expansion rate, the acceleration rate, and the, that's about it, and the age. And you can get kinematics, such as the angular diameter distance, luminosity distance, and so on. The very useful probes of, a lot of those are being used to probe the dark energy content right now. But that's just assuming there's no fluctuation in the universe at all. Now, that's not the whole story, obviously, otherwise we wouldn't be here. So the sort of second out of the three part of the calculation is called the linear perturbation theory. And that's where you start out with a homogeneous isotropic Robertson-Walker-Friedman metric, and you try to perturb it a little bit, assuming the perturbation is much less than 1. And that's a well-known theory now, and most of the CMB predictions come out of that. And I want to spend a few minutes briefly reviewing this theory and how the calculations are carried out. The third regime is the more difficult regime where things go nonlinear. That is when the fluctuation levels go above unity. Then perturbation no longer holds, and you cannot drop the second or third or fourth order pieces. Then all hell breaks loose, and then you either resort to numerical simulations or various spherical top hat collapse models and so on. And there will be more lectures about this later. So I would like to now review the linear part of the theory. And the idea here is whatever mechanism there is, for example, quantum fluctuations during inflation, that give us a primordial fluctuation, then however minute the level was, the primary mechanism for growing these fluctuations is through so-called gravitational instability. The fact that if you have a slightly overdense regions compared to the cosmic mean, it will grow bigger. And if you have a slightly underdense regions, that will become more empty. So this instability will help the contrast in the energy, in the density fluctuation to grow. Schematically, I'm talking about such as fluctuations of 10 to the minus 5 level, which is well in the linear regime, at recombination can grow to, this is a poster child, sort of a beautiful Abel cluster showing you many, many elliptical galaxies in this very rich cluster 2218. And and there are various lensed arcs here and so on, which allow us to map the dark matter distribution in this cluster. And the overdensity of matter in objects such as this could be order of 10 to the 5 or even more versus 10 to the minus 5. So there's a huge amplification due to gravitational instability. And the linear regime of this can be calculated using the perturbation theory that I will discuss next. So this is the nearly smooth universe. So the basic concept here is we solve the linearized coupled Einstein and Boltzmann equations. And by solving this, we obtain time evolution of fluctuations in the space-time metric that comes into the Einstein equation and the density fluctuations in whatever universe you want it to be made of. In the standard, this model I'm talking about, that of course includes dark matter, baryons, photons, neutrinos. Okay, dark energy really, for the most part, is smoothly distributed in space, except on very, very large scales. So dark energy only enters through the 0th order of the Friedman-Robertson-Walker metric. So it affects the overall growth and so on. I'll talk a little bit more about that. But it doesn't come in directly in the perturbed quantities here. Although if you want to know how dark energy fluctuates on very large scales, it is all part of this calculation. Okay, so So I want to just define a few of these perturbed quantities. For this talk, I'll just limit my perturbations to the scalar modes, although there could be vector and tensor modes in particular that the tensor modes are very relevant for gravitational wave predictions. Okay, but for now, I just want to write down the metric. And this is a particular gauge I'm using called the conformal Newtonian gauge. And here you're seeing two perturbed metric, phi and psi. Okay, so if they were 0, then we just have the homogeneous isotropic Robertson-Walker expanding universe where A is a scale factor. Now, phi is the familiar Newtonian, the counterpart of the Newtonian gravitational potential. And psi is the second scalar perturbation required to describe the scalar mode of the perturbation completely. The difference between the two is not big. And phi minus psi is the non-zero component of that is usually it comes from the anisotropy, the anisotropic stress tensor, which massive neutrinos can contribute to that. Okay, but for the most part, phi and psi are very similar. So this is the metric perturbation we would like to keep track of. And then, of course, there is the source of energy and momentum in the universe that comes with that. So for the density, this is the well-known density contrast. I just want to define this here. So at every time, every point in space-time, this is just the fractional difference from the cosmic mean. And here I'm using omega matter, whatever, 0.3 and h 0.7. So the cosmic mean matter density is about 10 to the minus 6 protons or hydrogen atom per cubic centimeter. And then there are higher order quantities we keep track of. For example, the velocity perturbations. And for this purpose, one can actually just keep track of the divergence of the velocity field because the curl part decays with expansion, so it's not very interesting. Okay, so we have phi psi delta theta and so on to keep track of. So we would like to have some equations that will govern their evolution. That's the key. We want to know how these things start with some initial conditions and how they evolve with time as a function of length scale and time. So as I mentioned earlier, these are the two main equations that go into the linear calculation. The Einstein equation, on the left-hand side, this involves the little g mu nu's, which involve a messy first, second derivatives of the metric perturbation. The right-hand side, the energy momentum tensor, that's where the source fluctuation comes in. Okay, so the delta, the theta, the matter, and radiation fields come into the right-hand side. So without writing down all the messy equations, I think it's sufficient for this lecture to just keep in mind that the left-hand side of the Einstein equation involve terms such as phi psi, phi dot, psi dot, and so on. And there are a number of these equations. And the right-hand side involve all the perturbed quantities. And here we keep track of the fields separately because they have different physical properties. Cold dark matter baryons, photons, neutrinos, massless and massive, and the velocity fields for each one, and so on. And the fact that it's linearized means we throw away anything that's order theta. Any of product of these quantities are higher order, we just throw them out. Now this equation clearly is not complete because it tells us how in the presence of fluctuations in the matter density and energy field, we need to have an accompanying set of equations describing how these quantities evolve. And that's what the Boltzmann equation does for us. Right? That's why these two sets of equations are coupled. So the Boltzmann equation really is an equation describing the phase space distribution of particles. And out of these particles, some are collision-less and some are collision null, although you could make cold dark matter collision null in some way if you like. And that's why this theory is so robust. You can basically, if anything you want to add, if you want to add a new component to your universe, first thing you will go is to go to these equations and figure out what equations to add to this big theory. But in the conventional collision-less cold dark matter case, its phase space distribution is governed by the collision-less Boltzmann equation, and so are the neutrinos. But the collisional ones are such as baryons and photons. They're coupled via Thomson scattering and other processes, which Wayne will talk about shortly. So this is a massive set of equations. And they are actually 7-dimensional equations because they depend on 3 positions, 3 velocities, and time. So in practice, they are very, very hard to solve. Okay, basically impossible. So you need to, numerically, you need to make some advance in solving these Boltzmann equations. So one standard trick is to take velocity moments of the phase space distribution. So the 0th velocity moment would just give you the density contrast. And the first velocity moment will give you the sort of average fluid velocity. The second velocity moment will give you the anisotropic shear of the velocity fields. And you just keep going on. It's actually an infinite order of velocity moments you can take. Okay, so schematically, this is what happens when you take these velocity moments of the Boltzmann equation. You get a bunch of equations where the sub-i's here label the particle species, cold dark matter, baryons, photons, and neutrinos. Okay, so each one you get its own equation. So for cold dark matter, it's just a boring collisionless equation. It's just a conservation law, really. Okay, so delta dot is related to theta of cold dark matter, and with some metric perturbation coming in. But this is only the 0th order velocity moment of this giant Boltzmann equation. The first velocity moment, as I mentioned, gives you the sort of the diff of v. So you get a theta dot, and on the right-hand side, you have all these delta for the density contrast, the velocity perturbation, and then now sigma is the shear, the second moment of the velocity of the phase space distribution. Okay, remember, I here labels the particles. They each have their own sigma sub ij, but I don't want to get into the details here. And then, of course, sigma, the shear tensor itself, has its own evolution equation. And then you can imagine now the right-hand side will have the third moment coming in. The one nice feature of this is the moments are only coupled to one lower and one higher moment. Okay, so theta, which is, I call it first moment, you only have 0th order, its own, and one higher order coming in, and so on. So this thing theoretically goes on forever. But when we actually do the calculation, we truncate it at some very high, what I call L. Okay, and you can test whether your truncation scheme doesn't lead to spurious effects at low moments. These are the important moments that we keep track of. So the bottom line here is now you see we have a nicely coupled linearized equations, and where the phi and psi's are evolution is governed by the Einstein equation, and the delta theta, the matter radiation field, velocity fields, and density fields are governed by the Boltzmann equation, and they're tightly coupled. I mean, they're just physically coupled in these equations. And since it's linear, okay, that's the nice feature of linear theory is even though each quantity depends on x, y, z, and time, we can actually do the calculation in Fourier space. And since it's linear, all the modes are uncoupled. So you can solve all the wave numbers, different wave numbers simultaneously. So for pedagogical reasons, I thought I would just show you one of the outputs of such a calculation. And what I'll show you is the most important quantity, the deltas for these different fields, and how they evolve as a function of time. And this is coming from a post-Kobe model, which we no longer study, but the features are the same. Okay? This was a cold plus hot dark matter model that we're very interested in lowering the excess clustering in the good old cold dark matter model. So there's no lambda here, but that doesn't really matter here. I want to just show you how the different particle species evolve as a function of time as an output of this, these CMB Boltzmann code. Okay, so this is an unnormalized delta as a function of the expansion factor. So today is here. And this is for a particular K mode, as I mentioned. You can do this for many, many Ks, as many as you want to. And there are actually 5 curves here. Okay. So what's important here is there is the so-called horizon crossing time. So for a given wavelength of perturbation, if you look at this in co-moving coordinates, then that wavelength is fixed. But the horizon goes like t, so that actually grows faster than a. So the horizon actually will catch up to this particular wavelength at some time. Or another way to see this is this wavelength enters horizon, okay, at some time. And this is actually horizon crossing for this particular mode. And before horizon crossing, when this perturbation is superhorizon, the time evolution depends on the gauge. So this is conformal Newtonian gauge. If you're interested in the synchronous gauge, which is one of the standard gauges people do calculations in, these deltas will actually grow outside of the horizon. But that's really not very interesting for us here. What we want to see is what happens when these perturbations enter the horizon. And that's when it happens. And once the perturbation enters the horizon, then microphysics comes in. So different species start to behave differently. And you see this very nicely, smoothly rising one, and you can easily guess that's the perturbation in the cold dark matter. Okay. And I just want to draw your attention to this slight actually difference in the power law. Okay, this is a standard CDM model, so omega matter is 1, and so no lambda. So at late time, the growth of delta actually is proportional to delta, to A, this expansion factor, and this is a well-known behavior that you can calculate simply analytically. But the earlier time, during the so-called radiation-dominated era, the growth is actually logarithmic, so it's suppressed. Okay, this will be very important when I show you momentarily the power spectrum of cold dark matter type of models. And the concept here is, as you well know, today's energy density in matter is way, way larger than the energy in radiation, right? Omega and gamma today, in photon today, is tiny. But since the radiation falls off like a to the minus 4, and matter falls off like a to the minus 3. If you extrapolate backwards in time, there was at one point the radiation and the matter energy density equal each other. And before that, radiation dominates. After that, matter dominates. And that's called the radiation matter equality time. And any modes of perturbation that enter in the radiation dominant era, such as this mode, its growth in the cold dark matter will be logarithmic. It's suppressed. And it has to wait until the universe becomes matter dominated when its growth starts to pick up. Okay. So if I chose a different wave number, like a very small wave number, a very large wavelength, that would enter the horizon in the matter dominated era, then it would never experience this suppression. Now, there are 4 other components here, and you can easily see probably that this tight coupling between photons and baryons. Right after the wave enters the horizon, these 2 curves are tightly coupled via Thomson scattering. And then you see the silk damping part. And at decoupling, that's when the photons and baryons photons are freed up from the baryons. So then these 2 curves start to diverge. Okay, and the baryon one is this sharply rising one. And what baryons do after decoupling is they are no longer stuck to the photons, so they look around, and immediately what they do is they fall into the potential wells already formed by the cold dark matter. See, cold dark matter has had a lot of time to grow while these 2 components fight with each other. But immediately afterwards, the baryons start to fall into the CDM potential wells, and they catch up. And photons, meanwhile, after decoupling, they just don't do much of anything other than the secondary anisotropy, anisotropies, which are very important. But for the primary, for the primary, they just, look, they're really boring. They just diffuse away and through a phase mixing. So you can see the amplitude, it really decays away. Now, there are neutrinos I would like to just briefly talk about. So for mass-less neutrinos, they are collision-less. So they are very much like photons after decoupling, except one is boson, one is fermion, but it doesn't really matter here. So one of these curves, which you probably can't even see, came into the horizon and you just started to damp away. Okay, so the fluctuation in the massless neutrinos, again, is very small. However, massive neutrinos play an interesting role, and how it behaves depends on its mass. So in this particular model, which is about 5 eV, okay, a neutrino mass of 5 eV, you see one of these curves coming in. Again, when it enters the horizon for this given mass, it was still relativistic. Okay, important concept for massive neutrino is that even though they have mass, whether they behave like relativistic or non-relativistic particle depends on how MC squared compare with KT, the photon temperature. So at very early time when KT is very high, the neutrino mass is negligible, then they behave like relativistic particles. And that's what happens for this particular neutrino mass. They come in and they, again, phase mix, just like the mass of the neutrinos. But when M is comparable to T, at some time, you can see from this plot, it happens around here, then they start to behave like massive neutrinos, which means they start to behave more or less like CDM. Okay? Then they, again, then their perturbations can grow, but because of this huge suppression at early times, they never catch up exactly. Okay, this is the amplitude. And this is the key character of any kind of free streaming or relatively warm and hot dark matter. Neutrinos are often called the hot dark matter or warm dark matter if they're fairly massive. The key is they suffer from sufficient free streaming that at late time they do cluster, but their clustering level is not quite as large as the cold dark matter. And again, I'll show you a power spectrum comparing cold with warm dark matter in a second. So the nature of the dark matter definitely matters in terms of the evolution of its perturbation. Okay, just to tie in with Wayne's talk shortly, so in this calculation, you get the fluctuations in every component you want, along with the metric perturbation, and you do this consistently. So it's a consistent full theory to linear order. So you get the photon fluctuations here too for a particular wave number, but you can solve this for all the waves and you get the entire power spectrum. So you get, in addition to the density power spectrum or the matter power spectrum, you also get the radiation power spectrum, and which is often cast in the angular fashion. So those are the angular temperature fluctuation power spectrum from the CMB. Okay? So it all comes out of this theory. So now being able to calculate these delta, evolution of deltas for a given mode, we would like to have a simple way to summarize their statistics. So I just very briefly review two important statistics that characterize the density fields. Okay, so there is this well-known two-point correlation function that's a product of two density fields at two different space coordinates separated by separation r. So Cassie is an ensemble average of these density fields. And in physical term, Cassie basically tells you the probability for finding a pair of particles separated by distance r, okay, the probability above Poisson, above random. So if your things are all randomly distributed, then Cassie is 0. And Cassie usually is a function of r, being larger for small r and dropping off sort of like a power law as you go to wider and wider separation. And Cassie really is not limited to the density field. You could talk about the two-point correlation function of galaxies and so on, and Carlos will talk a lot more about that later in the lecture. But this is a definition of Cassie. And its Fourier transform is the well-known power spectrum. Okay, in K space, so delta is a Fourier transform of this. It's exact, so P of K is exactly the Fourier transform of Cassie of R. Now, if your density field is Gaussian, which is predicted by most inflationary models, not all, but most inflationary models, then for a Gaussian density field, power spectrum uniquely specifies the statistics of the density field. No other correlation functions are needed. They're all 0. However, that's true in the early universe, but we know that today, the density field, if you look at this at low redshift, it's not Gaussian, even if the primordial fluctuations were Gaussian. And the reason is nonlinearity will couple the different modes and will introduce non-Gaussianity. Okay, so you can have non-Gaussianity either from the primordial spectrum, if you have certain, certain models, or at late time, you always get non-Gaussianity due to nonlinearity. So this statistic does not uniquely specify the distribution of galaxies or the density field at late times. Okay. So one way to describe that I'll just touch on here is the natural extension of the 2-point correlation function as the three-point correlation function. That's the lowest order statistic for a non-Gaussian field. And that by extrapolation of the previous slide, it depends on, so now we're measuring the sort of the clustering power of triplets, 3 points in space. Okay, so it forms a triangle. So now we have, instead of a separation, we have the 3 sides of a triangle to keep track of. And its Fourier transform is called a bispectrum. Okay, it's not a trispectrum. The Fourier transform of the 3-point correlation function is the bispectrum, okay, curiously. And here now it depends on 3 Ks, and the B is the counterpart of P, the power spectrum for the 3-point statistic. And there are various attempts at measuring these higher order quantities based on galaxy surveys, and you can do this in simulations and so on, or even on the CMB to test for the primordial Gaussianness of the fluctuations. Okay, so now I just spend the last few minutes elaborate on the power spectrum. Okay, so for the standard lambda CDM or CDM type of models, what is the power spectrum? I just want to review this because that will come into various talks later on, including Simon's when he talks about the Preschechter framework. Okay, so I just want to remind you that the P of K that I just defined, okay, again, there's a linear regime and a nonlinear regime, as I talked about earlier. For the linear cold dark matter power spectrum, it can be characterized by an amplitude, okay, a primordial piece which goes like k to the nth power, where n is the spectral index, and a transfer function which is 1 for small k, and it will do whatever the cold dark matter or dark matter tells it to do at higher k. Okay. So the way to view this is, so this is P of k, so it actually has units of volume versus k wave number. So this is large wavelength. This is small wavelength. And this is a well-known CDM power spectrum. I want to just point out 3 features, which is at a very large, on the very large scale, very small k, this is the primordial feature. And n equal to 1 is the Harrelson-Zeldovich power spectrum. And most inflationary models predict n approximately 1. So this part is preserved. But you see that it doesn't go on forever. And this shows you the power spectrum at 3 redshifts, calculated from the Boltzmann code I mentioned just now. So you see this characteristic peak where things bend over. And that peak is due to the radiation matter equality that I just mentioned when I show you the individual evolution of delta at a given mode. Right? So the way to look at this is a calculation of many, many k. From that calculation, and you compile the result here as a function of wavelength. So the peak where this happens depends on the horizon size at matter radiation equality, which is proportional to omega in matter times the Hubble constant squared. Okay, so again, the way to read this is higher k is smaller wavelength. And as I mentioned earlier, smaller wavelength enter the horizon earlier because the horizon catches up earlier. Okay, and so these modes on the right all enter the horizon when the universe was still radiation dominated. And during that time, the delta perturbed field in matter can only grow logarithmically. So they're suppressed relative to the modes which enter in the matter-dominated era later on. And those modes just grow linearly if you do a standard CDM model as a function of expansion factor. So these can grow relative to those. That's why you get this characteristic bending over.
Can you explain what's the physical mechanism by which the cold dark matter growth is suppressed by the radiation?
It's basically because if you solve the evolution equation, the radiation component dominates because rho in radiation comes in front of a piece, and rho in matter comes in front of another piece, and the first piece simply dominates. So the growth in the non-relativistic component is basically frozen. Okay. We can talk more if you like him. So for cold dark matter, power spectrum has this well-known k to the minus 3 slope for very high k. But if we modify the nature of cold dark matter, this part of the behavior can change, and I'll show you it in a second. So in summary for this slide, for the linear matter power spectrum, is the shape depends on things like omega matter. Okay, in this case, for example, omega matter, if you decrease omega matter, then you have to wait for radiation, you have to wait longer for radiation to equal the matter. So the radiation matter equality happens later. So the horizon size is larger, and corresponding k is smaller. Okay, that's why when you decrease omega matter, this peak moves to the left. The shape depends on omega matter and the nature of dark matter. But I want to point out that important feature here is the growth rate, which I will not derive, but it's easy to do. The growth rate really depends on all the kinematic, all the zeroth order of the Freeman-Robertson-Walker metric comes in here, or the Einstein equation. So the growth rate is well known to depend on omega matter, as well as the dark energy content and other parameters in the cosmological model. Okay, so so for example, when omega lambda is non-zero, the late time growth of P of k is slower than a model where omega lambda is 0. So using the growth factor is a very powerful technique, along with the angular diameter distance and so on, to probe the value of omega lambda. Okay. The shape itself really is mostly determined by the dark matter component. Okay, so just a couple extension of this review is one, as I mentioned earlier, if you're interested in different type of cold dark matter, for example, warm dark matter, these are considered to be some sort of massive neutrinos. Okay, so you can use the same calculation, except as you saw earlier, when neutrinos have mass, especially when the mass is small, they were highly relativistic earlier on, right? So their growth is suppressed, so their free streaming distance is quite relevant here. So you see, so this figure is just like the other figure, except this is very much, I'm only showing the right side of this figure. Okay, and this is also at redshift 3 because we're interested in alignment alpha forest here, but that doesn't matter here. I just want to show you the relative power in the power spectrum. So this is the right side of the previous plot at a higher redshift, 3 here. And this is the standard CDM model prediction. So you can see this is one deck this is about 3 decks, so this is k to the minus 3. But if the dark matter has a, say, 200 eV neutrino, if it's not cold dark matter, but instead of warm dark matter, there's this very large suppression, meaning the fluctuations are wiped out on this free streaming distance, okay, scale. And then when you vary, there are sort of 4 curves here. Don't worry about this long dash one. That's some kind of broken invariant power law, power spectrum. But if you look at these 4 sort of monotonically changing ones, this is 200 eV, this is 500 eV, 750 eV, and 1K eV. Just showing you that as you vary the warm dark matter mass, when you raise it, it gets to be more and more like a cold dark matter. Okay. And the physics here is free streaming. Now, I just touch on that even neutralinos themselves have an intrinsic free streaming distance that is not shown here, but it has been calculated to correspond to about, I don't know whether the K is some huge number, but the corresponding mass is about Earth mass. Okay, about 10 to the minus 6 solar masses. And that's very relevant for the very first formation of objects in the CDM model that Simon will talk about.
Is it non-collisional? Warm dark matter is assuming it to be non-collisional?
Yeah. This is definitely some kind of, it's not a standard model neutrino. Yeah, those have been constrained to be like fraction of an eV. So these are some kind of stereo neutrinos or whatever exact neutrinos you want. Okay, so very last slide I'll show is, here I've still been talking about the linear perturbed power spectrum. I just wanted to show you what nonlinear power spectrum looks like. Okay, and I'm back to the previous CDM model, but here on top of the linear power spectrum, I'm showing the power spectrum calculated from an actual n-body simulation. Okay. So the power spectrum is not just important for characterizing the cold dark matter or the nature of the dark matter. This is actually used as the input starting point for the initial conditions of n-body simulations. You want to start your n-body simulations when your modes are still linear. Okay, so you use this to set up the initial displacement of your particles in the simulation from a regular grid. You displace that according to the P of K of the model you're interested in, and then you evolve that. And this is a standard output from a very small n-body simulation, but it shows you how so this is determined by the box size. You have a 2 pi over L. That's the largest wavelength you could sample in your box. That's why it's a Nyquist frequency here. Okay, so you cannot sample anything bigger than that. But you see higher, and the highest part is limited by the spatial resolution and mass resolution of your simulation. But the key message I want to send here is, for the lowest Ks you can sample in the simulation, it's still following the linear evolution, which is great, which is very important, which says your n-body code is partially right, at least. Okay, you want them to follow the linear evolution. But then you see this important deviation from the linear theory prediction because of the nonlinear, all the nonlinearity. In the smaller scales, the deviation becomes larger and larger. Okay, so this, and you can do the same thing for the bipower spectrum and so on. And there are various other ways to approach the nonlinear regime, which I and Simon and Carlos, I think, will talk about today and tomorrow and later on. Okay, so I think I'll stop here. Thank you very much.
So, are there any questions? It's not possible. Are there any questions?
Has the free streaming mass, those warm neutrinos, those very, I guess they're exotic, have those